All right, we'll begin. Just a couple notes. I'll get those quizzes graded and I'll post those scores up. Again, if you want to review your quiz, see what questions you got wrong or anything like that, just send me an email saying I would like to look at my quiz, and that way I can pull your quiz out of the stack and have it ready for review during office hours. So again, just send me an email and I'm happy to do that for you. But if you don't send me an email, I won't have your quiz ready for review. So if you want to look at your quiz, just send me a message there. All right, we will continue on in our section on descriptive statistics. So descriptive statistics is all about learning how to describe sets of data. Okay, so in the big picture of statistics, we want to be able to make conclusions about the population based on a sample of data. And in order to do that, we first have to be able to describe our sample of data. So these first few weeks are all focused on descriptive statistics. We're learning how to describe our data. Okay, and so just to kind of recap where we've been, so we'll say, in the big picture is we want to make conclusions about the population based on a sample of data. Okay. In our first section is descriptive statistics, where we learn how to describe our data. Okay. And so we've learned how to, for categorical data, we can describe with a frequency table. We have frequency tables and relative frequencies, which is pretty much a proportion. Okay, and we can also display with, what can we use to display categorical data? Yeah, I'm asking you. What can we use to display categorical data? A bar chart, okay. All right, and for numeric data, we have summary statistics. Okay. What are some summary statistics? How do we describe numeric data? So I'm asking about summary statistics. You guys are mentioning some displays, but if we wanted to describe numeric data and you can't draw a picture for someone, maybe you're trying to describe a set of numeric data over the phone.
Frequency?
Not for numeric data. What do we use? Okay, so summary statistics, we can describe center and we can describe spread. What can we use to describe the center? The median and the mean. Now what is the difference between the median and the mean? So the median is what?
The middle point.
The halfway point. And what is the mean?
Pretty much the average.
It's the balancing point. And to describe the spread, what do we have? We have the IQR, and we have the standard deviation. Okay. Of these summary statistics, which ones are affected by outliers or extreme points? The mean and standard deviation are affected by extreme values. What's another word for extreme values? Outliers, okay. And which ones are not affected by extreme values? The other two, the median and IQR, are not affected. Okay, so this is how we can describe numeric data. And if we wanted to display numeric data, how can we display numeric data? So we have, yeah, I've heard you guys say them. We have dot plots, we have histograms, and box plots. Okay. If we talk about a distribution being skewed or symmetric or something like that, are we talking about numeric data or categorical data, or could it apply to both?
Numerical.
So if we're talking about data being skewed or symmetric, we have to be talking about numeric data. Okay, so shapes, describing the shape of a distribution, we're talking about numeric data. Okay. Okay. So this is kind of where we've been so far. We're just learning how to describe data, learning kind of the summary statistics, some of these tools that we have available to us to describe data. And today we're going to cover more on this section on descriptive statistics, and we'll be talking about describing a relationship between two numeric variables. Okay. Okay, so what does it mean to describe a relationship between two numeric variables? Well, imagine you've collected data on multiple, on a sample. Okay, so imagine we have a sample and we're collecting data. And when we collect data, we are collecting multiple pieces of information, okay? And in part, we are collecting data on two numeric variables, okay? So for each observational unit, we are collecting at least two numeric variables. Okay, so just for example, perhaps we are looking at a certain species of snake, okay? We look at a bunch of snakes of a certain species. Okay, so this is my picture of a snake. And then, for this snake, we're going to gather two pieces of information, okay? So we're going to gather, one variable is the length of the snake, and then we're going to measure its weight. Okay. And then we get another snake, all right? And this snake looks like this. Okay. And this one we also measure its length and its weight. Okay. And we look at a bunch of these snakes, okay? So we have more, and for each snake we're going to measure its length and we're going to measure its weight. And we have a question. Is there a relationship between the length of the snake and its weight? Okay, and what do you guys think? Okay, and what kind of relationship can we expect to see?
The more length, the more weight.
Yeah, we can, so the relationship, okay, so we will see a relationship that shows that snakes that are longer will generally weigh more, and snakes that are shorter will generally weigh less, okay? Right, and that seems to make sense, especially if we're talking about, you know, for one particular species, we would expect to see something like this. Yes, question.
Can we just call this positive correlation?
Yes, we'll get to that. Okay, so we'll say there is a positive correlation, but yeah, just for now we're just kind of using these simple terms of showing what kind of relationship we expect to see. Okay, and so here for the relationship between the length and weight of a snake, we expect to see that snakes that have higher length will have, in general, have higher weight. Snakes that have lower length, in general, will have lower weight. Okay. And this is just a very loose definition. Okay. And so what we will learn in today's chapter is we will learn to quantify this relationship. So just like before, last week we talked about the spread, and we said, you know, the Baker family children had high spread in ages and the Adams family children had low spread in ages. But rather than just saying high spread and low spread, we were able to quantify that using the standard deviation and give it a number. So in the same way, with the relationship between two numeric variables, we will learn to quantify it, and we will assign a number, and that's going to be called the correlation. And then we will also learn to model the relationship so that if we have one of the variables we can make a prediction for the other variable. Okay, and so that's what we will learn to do in today's chapter. Okay, so today, we will learn to describe a relationship between two numeric variables. And the key parts are the shape, the direction, and strength. Okay, we will quantify the relationship. I'll say, yeah, we will quantify the direction and strength of a relationship. With what we call correlation. And then we will create a simple mathematical model of the relationship. So we can make predictions. Predictions and estimates. Okay, and this is called linear regression. Okay, so let's talk about describing the relationship using the shape, or describing the shape, direction, and strength of a relationship between two numeric variables. Okay, so again, it's very key that we're talking about two numeric variables. So we cannot, so the stuff we learned today cannot apply if one of the variables are categorical, or you have, more than two variables to look at. So we're looking at just two variables, or if you have less than two, it's not going to work. It's got to be two variables, and they both have to be numeric. Okay, so we have the shape of a relationship. Okay, so let's talk about the shape of a relationship. So the relationship can either be linear or nonlinear. Okay, as far as this class goes, we're going to either classify them as linear or nonlinear. Linear means a straight line can describe the overall relationship. And nonlinear means a straight line is not sufficient. Okay. Now, in order to talk about this idea of shape, we have a tool for displaying, okay? Tool to display two numeric variables, and that is called the scatter plot. Okay, and so, we are, you have an x variable and you have a y variable, okay? And you're basically plotting coordinate pairs. So, we could survey people and we could ask different people. We can have person 1 and person 2 and person 3 and so on and so forth. And we could ask them for two numeric variables. We can say, what is your height? And what is your weight? Okay, and so arbitrarily I will just assign height to X and weight to Y. Okay, so maybe person 1 is 70 inches tall and weighs 170 pounds. And maybe person 2 is 65 inches tall and weighs 140. Maybe person 3 is 62 inches tall and weighs, I'm just making up numbers here, 125. Okay? And so on our thing, we might have marked off a number line. For height. And then as far as weight goes, okay, and we would just plot coordinate pairs. So person 1 would be at 70 inches, weighing 170 pounds. This person is a dot right there. 65 at 140 would be right there. And then we have 62 at 125 right there. Okay, so these are the three dots that I have included here, and we can gather more data. And I'm going to just kind of draw some more dots. And so, because you can have people with high weight and low weight at any of these things. Okay, and if we look at the overall trend here, looking at kind of the relationship between X and Y and the dots, we might say that there is overall a linear trend. Okay, something that looks like this. Okay, and so we could say that the relationship between height and weight is linear. Okay, because overall there's a straight line might be able to summarize the general trend between height and weight. Yes, question?
Let's say we only had those 3 points.
Yes.
You can't really draw a straight line between the first point and the last point, right?
If we only had 3 data points, I would and you wanted to create a linear model based on the 3 data points?
Yeah.
And what's your concern?
No, my question is that let's say that the point that it has the height of 65 and the weight of 140 was a little bit lower, just to take the doubts out, and you wanted to draw a line between the one weight 62 to 70, of course, to pass at a 65, and it does not create a straight line.
So that is not how we create linear models. Okay, we don't just pick the two extreme points and draw a line to connect them.
3 points.
Or 3 point. We don't just pick.
It's a trend.
We don't pick dots and just draw a line to connect them. Okay. We'll talk about how the linear model is determined. Okay. but it's not just, it's not in the process that you've described, okay? Right now, I'm just saying that the overall trend can kind of be summed up with a straight line, okay? And of course, not all the dots will follow this line perfectly. You're gonna have some people above the line, some people below the line, and things like that. But overall, we are seeing, in general, people with higher height weighing more, people with lower height weighing less, okay? We are not seeing, and don't put this in your notes, but we're not seeing something that goes like this, or we're not seeing something that goes like this, or we're not seeing that, okay? Those would not be linear trends. We're seeing something overall looks like a straight line works, okay? We could, you know, here are examples where the shape is nonlinear, okay? So we have a nonlinear shape. Let's say we wanted to plot someone's age, okay, versus their height, okay? So in childhood, perhaps you see a linear trend. As the kid gets older and older, the kid grows taller and taller, okay? So maybe you see something very linear, but as the kid approaches adulthood, you're gonna see someone's height remain the same, okay? And so in this case, a straight line does not work to sum up the entire picture, right? So this is age versus height, okay? So perhaps if we looked only in childhood, we might see a linear trend, okay? So if, you know, in childhood, the relationship appears linear. Relationship between age and height is linear, okay? But overall, the relationship is not linear. Okay, a single straight line does not describe the relationship. Okay, because if you were forced to pick a straight line, you know, what would you do? Would you do this? Or, you know, would you do this? Or would you do this? You know, who knows, right? Like, a single straight line is not going to work, okay? So that's just a simple example of a situation where a linear relationship doesn't work, okay? You might have data that goes like this, okay, where the overall relationship looks something like this. I don't know what this is, X and Y, okay? So again, nonlinear. Or, you know, these are all examples that are nonlinear, and you could have something right? And so, you know, each of these things, you know, you got kind of this business going on, and over here you got this, I don't know, kind of funnelish looking thing. Okay, both of these are all nonlinear relationships. So as far as this class goes, we're only going to look, or we're only going to learn how to describe linear relationships, okay? If you see something and it's nonlinear, all you're going to be able to do is say, this relationship is nonlinear, and that's that, okay? If you were to take a more advanced statistics class, you could learn how to describe nonlinear relationships. But as far as an intro class goes, linear it is. Yes?
How many other roughly types of nonlinear are
I don't know, lots, okay? So that, you know, you can have exponential, quadratic, sinusoidal, I don't know, there's lots, okay? So who knows, okay? Okay, so we've got linear versus nonlinear. We have the direction or trend of the relationship. Okay, and so we have positive direction and we have negative direction. So positive means in general. Okay, and everything we say here is in general. Large values of x are associated with large values of y. And small values of x are associated with small values of y. Okay, that's a positive relationship. A negative relationship, we flip things around. So again, everything is in general. In general, large x goes with small y, and small x goes with large y. Okay, I guess I could be more formal and write large values of x are associated with large values of y, but I think you guys get the point, right? Okay, so if I say this is x and I say this is y, and I draw our data points like this, is this an example of positive or negative relationship? This would be a positive relationship because down here are these values large or small values of x? These are small x and these are large x. Okay, and over here we have small y and large y. So if we look at this, if we look at where the data is for the small values of x, we see that they are also near the small values of y. And if we look at where the data is for the large values of x, we see that they are also large for y. So this would be a positive relationship. This is okay. And so our example of snake length and snake weight was a positive relationship. So if we said snake length was x and snake weight was y, what we'd see is that values with high x, meaning large snake length, so long snakes, will be heavier, will be the heavier snakes. Snakes that are short, so small x, will be way less, so small y. Okay. And so if that is a positive relationship, then over here we have a negative relationship. Okay. So again, we have small x But if we look at where small x goes, it goes with the large y. So small values of x, and we look at where the data is for the small values of x, we see that they're associated with the large values of y. And the large values of x is associated with the small values of y. Okay, so here we have a negative relationship. Okay, and so one example here could be the mileage odometer reading on a vehicle versus kind of the resale value. So overall, cars that have high odometer readings, so cars that have many miles driven on them, their resale value will be lower than cars with low odometer ratings. Okay, and this will be especially true if you just picked one particular model of vehicle. So if you just said, I'm in the market, I want to buy a used whatever, Honda Civic or whatever, and you are looking around, in general you will find that vehicles with high odometer readings will have lower resale values, and vehicles with small odometer readings or low values will have higher resale values. Okay, and so those are what we are talking about when we say a positive or negative relationship. Okay. And lastly, we have the strength of a relationship. Okay. So a relationship can be strong or weak or anything in between. If the relationship is strong, then that means there is little scatter around the trend line. Okay. Another way to describe a strong relationship is that if you have a value for the x, okay, you can make good predictions for y. And on the other side, if you have a weak relationship, then there is lots of scatter around the trend line. Or in terms of predictions, if you have a value for x, you can still make a prediction for y, but you can't expect it to be very precise. Okay? So if you have a value for x, okay, your prediction for y will not be precise. Okay, so here I'm going to just put up two positive relationships. So here, this would be a strong relationship. Because if I have some kind of trend line, there's very little scatter around the trend line. Okay. Little scatter around trend line. And then let's say I pick a particular value of x, say right here, and I go up here and I try to kind of find my zone of prediction. My prediction for what y will be in this kind of small region, okay? Okay, so this is a strong relationship. Okay, over here, we can just produce a lot more scatter. Okay, and so here, we just have a lot, we have more scatter here. Okay, so this is a weaker relationship. More scatter, and then if I were to pick some particular value of x, say right here, okay, kind of our prediction zone would go all the way from here to here, okay? So we have a much bigger zone of prediction. Right. So does this make sense for what kind of to describe whether a relationship is strong or weak? Okay. All right, and so again, instead of just describing something as strong or weak, positive or negative, we can actually assign a quantity to it, okay? And that's especially useful for this strong or weak relationship, because the idea of what is strong and what is weak heavily depends on the context of the relationship, okay? So, you know, if you're talking about robots and machines, you would expect the relationship between, you know, two variables to be strong to begin with, and so the idea of what's strong and weak for robots and machines would be, you know, a kind of a different picture than if we were talking about people, okay, where people in general are much less predictable, and so you know, the context of what is strong or weak the usage of strong or weak depends on the context. So we're gonna learn how to quantify these things with a value, and that value is called the correlation coefficient. Okay, so much in the same way that the standard deviation or the IQR gives a quantity to the idea of spread, the correlation coefficient is a value, or correlation coefficient, you know, often just called correlation. okay, is a summary statistic that assigns a value to the strength and direction of a linear relationship. Okay, so the interpretations of the correlation will only make sense if the relationship is linear. Okay, and so how can we decide or determine if a relationship is linear or not? We have to plot it, okay? So we create a scatter plot and we just look at that, okay? And that's that's actually the best way to decide if a relationship is linear, okay? The best and really the only way that we're going to learn in this class, the best way to decide if a relationship is linear is to create a scatter plot and look at it. Okay. And if it looks like there's a linear relationship, then that's good enough, okay? Because our eyes and our brains have this really well-developed sense of identifying patterns, okay? So, you know, we see patterns everywhere we look, and if our brain says this kind of looks like a straight line, then that's a very good indication that the relationship is linear, okay? Correlation can be calculated. It's just the result of a formula. It can be calculated for nonlinear relationships, but if you calculate for nonlinear relationship, it just won't have any meaning, okay? So correlation can still be calculated or but it will not have any meaning or have a useful meaning. Okay. So the symbol for correlation is R, kind of like relationship. Okay, and R can take on any value between -1 and 1. So -1 is less than R, which is 1, so R can be any value between -1 and 1. the sign of R is the direction of the relationship. So what does that mean? If R is positive, the direction is positive, and if R is negative, the direction is negative. And if R is far from 0, or we'll start off with if R is near 0, the relationship is weak. And if R is far from 0, the relationship is strong. So far from 0 means near 1 or near negative 1. So this is correlation. Okay, correlation, the value R, it's just a way for us to quantify a linear relationship to say whether it has a strong relationship or a weak one, and whether it's positive or whether it's negative. Okay, so let's just draw a few examples here. Okay, so we can say X is, we can measure people's height in inches, and height in centimeters will be our Y. Okay, and so if you know someone's height in inches, can you predict their height in centimeters? Yes, and you can predict it perfectly, okay? If somebody is 72 inches tall, you can predict their height is exactly, you know, whatever it is in centimeters. And there's going to be no variation there, right? And so the R, the correlation here, would equal what? 1, positive 1. Okay? As soon as there's a little bit of scatter, the relationship is no longer 1. So here's a scenario where you've got, you know, just a tiny bit of scatter between X and Y. And so here R might be something like 0.98 X and Y. And so an example given in the textbook is, you know, we look at our sample as different countries, and we're looking at the X is the life expectancy for men, and Y is the life expectancy for women. And so what the graph shows is that if for a particular country you happen to know the life expectancy for men, you can make a pretty good prediction about the life expectancy for women, okay? You're not going to have a scenario where, you know, if in one country the life expectancy for men is 75, and in another country the life expectancy for men is 75. You got two countries where the life expectancy is 75. You're not going to have, you know, 50 years of difference between the women's life expectancies. We would we would probably predict the women's life expectancy to be like 78 for one country, maybe 79 for another country or something like that. So if you know the life expectancy for men, you can predict the life expectancy for women very well, but not perfectly. There's going to be a little bit of scatter. Okay. As the scatter increases, the R gets closer to 0. So here, you have R equal to, I don't know, 0.6. I'm just making that up. Okay. And here, this could be height versus weight. And it might, so overall there's a positive relationship, but if I tell you someone is 5'6", you can make a prediction for weight, but there's going to be a lot of, you can have two different people who are both 5'6", that and one weighs more than the other, and there could be a significant difference there because height tells you a bit about a person's weight, but there's more variation there. Okay. Are there any questions? Yes.
How do you measure R?
How do we measure R? Okay, so R is, there's a formula to calculate R, but we will not learn how to calculate R ourselves by hand. Okay, the formula is just, it's more tedious. And frankly, I would feel like I'm wasting time to try to kind of teach how to calculate R itself, okay? Today, we have computers, and computers will calculate R for us, okay? It's just you throw the numbers into a formula, but it's a tedious formula, and the computer will spit it out, okay? I don't have to teach you how a transistor works and the circuits of a thing in order for you to use your phone, right? We don't have to learn how to design a phone in order to use it. So we're going to just learn how to use R and understand that, what it means to have different values of R, but we're not going to learn how to actually calculate R ourselves. So R will always be provided in the problem or as part of, computer output, and you look at the output and say, oh, this is what it means, okay? So but is this okay as far as kind of the interpretations for R here? Okay, and then when you get to a certain point where there's just kind of complete scatter and there's no overall trend, here you can say R is equal to 0. No relationship between X and Y exists. Okay, and these were all positive examples. Let me just show you a couple. As soon as they start trending in the opposite direction, then you would have negative R. Okay, so something that looks like this, what would we kind of guess the value of R to be here?
0.8.
Yeah, so R here I would say is like negative 0.95. Okay, there's just a little bit of scatter. Okay, little scatter, but in the negative direction. Yeah, I'm just kind of eyeballing this, right? But if I have this, and so if these are all in a perfect straight line, what do we have?
-1.
Yeah, R here is -1. Okay, so again, there is a formula for R, but we will not learn it. Okay, R is almost always calculated using a computer. So we will just have to learn how to interpret R. Interpret and use R. Let me just check our understanding here. So okay, what is the R here? 1. R here is 1, okay. What if we have another data set? Where they're still in a straight line, but the slope is less steep. What is R here? Huh? It's also 1, okay? So R is not affected by the slope. What affects R?
The relationship between...
What about the relationship? The strength and direction. Okay, here, what is, so if we have all the dots flat, what is R in this case?
1.
R is 0, okay? Because it's neither positive nor negative, okay? There's actually no relationship between X and Y, okay? This could be, for example, we could ask someone, how tall are you? X could be height, and Y could be, how many fingers do you have? Okay. And I realize not everyone has 10 fingers, but you know, let's just assume you got a small sample. Okay, so maybe you surveyed 50 people, and all 50 people you surveyed happen to have all 10 fingers. Okay, and so will you see a relationship between someone's height and the number of fingers? No. Okay, height and fingers, there's no relationship. You're going to have tall people with 10 fingers, short people with 10 fingers. So it would not be correct to try to create a linear model here. Okay, there's no relationship between X and Y in that scenario. Okay, let's talk about a few things about R, okay? So we'll say a few key points about R. All right, so the order of the variables does not affect R. Okay, so if the correlation between X and Y is some number, as let's say 0.53, then the correlation between Y and X, so switching the variables around, is also 0.53. Okay. Adding a constant to R, or I'm sorry, not adding a constant to R, adding a constant to one of the variables, one or both variables, and or multiplying the variables by a positive constant has no effect on R. So kind of another way to put this is changing the units of the variable will not change R. Okay, so if let's say correlation between height measured in inches and weight is 0.65. Okay, if you convert height into centimeters, the correlation will still be 0.65. Okay, correlation itself is a unitless quantity. Okay, it's always between -1 and 1. It's a unitless quantity. Okay, and again, this is very key. The correlation can only make sense if the relationship is linear between two numeric variables. And then lastly, correlation does not mean causation, or cause and effect. So two things could be correlated, but it does not mean that one causes the other. Okay, so these are just some important things to keep in mind when we're talking about correlation. Okay, let's take we'll take a 10-minute break here. Okay, and we'll get started at we'll say 8:52.